So this is chapter 18, and we will be talking about um, thermodynamics. It's entropy, free energy, and the free energy and the chemical equilibrium. So first of all, some processes are spontaneous processes, and those processes that um, happens or they occur under specific set of conditions without any outside intervention. So they happen by themselves, spontaneously. There is no need to do anything from the surroundings. The reaction happens by itself. But there are some reactions that will never happen by themselves, non-spontaneously. But it doesn't mean that they will never happen. It will happen if there are some other conditions. So they actually will happen. So let's say freezing of the water. Water will freeze when there is a right condition, or when there is a temperature which is 0 degrees Celsius. It starts to freeze, and below that, it's already freezing. So spontaneous means it happens without any outside intervention, help from anything. It's under specific set of condition. So, and that's an example in giving to you spontaneous process. When you take ice from the freezer and you put it on the table, at room temperature, it starts to melt spontaneously. You don't need to do anything for that. If you take a sodium metal and you will put a sodium metal in water, just the cold water, it will vigorously react and it will make hydrogen gas and produce sodium hydroxide. If you take a bowl and you will put it on the top of a hill, it will go spontaneously down the hill. Iron will rust at room temperature, and as I was saying, water will freeze, but the condition has to be a specific set of condition less than 0 degrees Celsius, let's say minus 10 degrees Celsius. The processes are non-spontaneous. Let's say water will non-spontaneous. Water freezing at room temperature, it would not happen, right? And if I will take sodium hydroxide and the hydrogen gas, they will never give me metal. It will never produce sodium metal and the water. That's the reverse reaction is not spontaneous. And if I have a bowl, it will not go spontaneously uphill by itself. And if we have a rust, it will not go back to become iron metal at room temperature, and spontaneously ice will not start melting when it's a negative 10 degrees Celsius. So some processes happens by itself spontaneously, some will never happen. So some under that specific set of condition. Well, it is said that if the exothermic, once again, the reaction that release energy and the delta H's are negative for the exothermic reaction. The exothermic reaction, they happen spontaneously at room temperature. So this is a methane. Methane will combust with the oxygen spontaneously. It will form carbon dioxide and water, and it will release energy. So hydrogen ion and OH minus, they will spontaneously react. Let's say it's a net ionic equation for acid-base reaction, and it will release energy. Those exothermic reactions are spontaneous. But this exothermic reaction, take a look at this liquid becoming solid. This exothermic reaction is not spontaneous when the temperature is above 0 degrees Celsius. As you can see, this process, liquid going to solid, yes, it will release the heat, but that will not happen when the temperature is greater than 0 degrees Celsius. So exothermicity, or the reaction being exothermic, it favors spontaneity, but if the reaction is spontaneous, it does not mean that that the only factor that will determine if the reaction will happen spontaneously or not. Another factor that actually affects the um, the spontaneity of the reaction is called entropy. Entropy. Entropy is the variable is S, capital S. The entropy of a system is a measure of how spread out or dispersed the system's energy is. So if the energy of the particles, like particles are moving around and they have a kinetic energy, if they will spread around, they will occupy bigger volume, then the entropy actually is increasing. As we have here, the greater the volume it occupies, the more spread the particles are, the more spread their kinetic energy are, the greater its entropy. So it says here that the spontaneity is favored by the process being exothermic, but the spontaneity also favored when the entropy of the system increases. So there are two factors. Actually, you can look at that and you can say, well, this reaction happened by itself. And keep in mind that it doesn't say if it will happen fast. It just will say, will it happen by itself? But we don't talk about how fast that will happen. That is actually is the kinetics. That's what the kinetics studies that. So, but if the reaction happens, you will see if the process is exothermic, if it releases energy, and if the entropy of the product is greater than the entropy of the reactant, then we will say that reaction has a possibility to happen spontaneously by itself. The quantitative definition of entropy, it was actually given by Boltzmann. It's entropy equals K. It's the Boltzmann constant. Uh, the W, logarithm over W. And the W is its number. It's the number of the energetically equivalent different ways that the matter can be arranged. It's the different state that the matter can be arranged. So S equals K, Boltzmann constant. So how the constant is derived, they will take the gas constant in joules and divide this by the number of moles. And that's what the unit of the entropy will be joule over the K as well, because W is just a number. It has no units here. So the more the more is the ways that the particles can be spread about, the more is the entropy of the system is. So the more arrangement the particles can be put, so then the more way you can arrange the particles, the more is the entropy increases. So we're not going to go into very details of the quantitative definition of an entropy, but for our purposes, what we need to know, you look at the reaction where the state of matter are specified, and you have to say, will the entropy of this reaction, will it increase or decrease? So that's where you can predict if the reaction will happen spontaneously. So as for any delta variable, delta of the entropy is the final entropy minus initial entropy. So as I said, we're not going to calculate this. But the standard entropy is the same as a standard enthalpy. So since we cannot determine the absolute value of entropy, so we can actually find the change of the entropy at the standard condition. And the standard entropy, it's the absolute entropy of the substance at 1 atm. So here you have to look at this one. If you remember from the Chem 11, standard enthalpies of formation of elements were equal to 0, but the standard entropy values of the elements are really not 0 entropies. So the entropies of everything, even the elements in a different state, solid, liquid, gases, they're not 0, because the particles are really moving around, especially if they're in a gas state. Do you see sodium in a gas state? It has much greater entropy, much greater movement of the atoms, and more ways those atoms can arrange themselves and can have a different position. So, so all of the compounds, the element, they all have their standard entropy values at like standard condition 25 degrees Celsius. If they're gases, the standard condition is 1 atm. If it's a liquid, it has to be pure liquid. Solid has to be pure solid. But all of them have the values. So that's what it's saying, that for the giving substance, the standard entropy is greater in the liquid phase than in the solid phase. So as you can see, the standard entropy of the sodium in the solid state and in the liquid state. So in a liquid state, it's greater, but in a gas phase, it's much greater than in the liquid phase. So if we have two substances in the same phase, which has similar molar masses, the substance which has a more complex molecular structure will have a greater entropy, standard entropy. And if we have elements which has a different allotrope, let's say carbon, it's a graphite, or it's a diamond, in the form in which the atoms are more free to move, it has more entropy. So if we will look at this general equation, how to calculate the standard entropy of the reaction. It's exactly the same formula that we did in a Chem 11. It is the sum of the standard entropy of the products minus the sum of this, the standard entropies of the reactants. So don't forget, you have to multiply by their number of moles if they have a coefficient greater than 1. So they're giving you the reaction, let's say A, and for the reaction A, calcium carbonate solid forms calcium oxide solid and the CO2. By looking at this equation, you just have to say that this equation will have, that equation increases the entropy of the system. This is a solid. And one of the product is a gases. So that means entropy has to be positive. So if we will plot into this, into the equation, the standard entropy of calcium oxide plus carbon dioxide, and then from that we will subtract the entropy of calcium carbonate, then we will see, as you can see from this formula, the delta S of this reaction A is a positive number. It is a positive number because entropy of the, you see on the product side, we have a gas, and the entropy of gases are much greater than the entropy of the substances in a solid state. That's why delta S is a positive number. For the reaction to have a positive delta S is one of the factor to for the reaction to be spontaneous. So there is a qualitative predicting the sign of delta S. How can we say what should be the sign, not the number, just the sign? Sometimes it's useful to know just the sign. Several processes, they will lead to an increase in entropy or melting, because in the melting you have solid changing into the liquid. Liquid, they have more entropy than the substances in a solid state. Vaporization or sublimation. In the vaporization, liquid changes to gas. In the sublimation, solid changes to gas. And in a gas state, particles, they occupy more space, more volume, they're spread around, their energy is spread around, and entropy is greater. Temperature, increase the temperature. Increase the temperature also gives the particles more kinetic energy, they move around, and they can occupy more spaces. And another one, if the reaction results in a greater number of gas molecules, that reaction also will have a positive sign of delta S. So this is just a sample problem. Also was given to you in ALEKS to predict, just to determine, predict the sign of delta S. Once again, the solids, calcium carbonate forms the gas, heating of the bromine vapor, increasing the temperature, condensation. Condensation, you actually have vapors forming liquid. That's actually should decrease the entropy of the system. Reaction of nitrogen gas and HCl to give NH4Cl solid. You see there are gases on the reactant side, and there is a solid on the product side that should decrease the entropy of the system. Dissolution of sugar in the water, that should increase the entropy of the solution. Okay, so entropy changes in the universe, calculating delta S of the surroundings, and second and the third law of thermodynamics. So delta S of the surroundings, you see that's a surroundings, it's proportional to the minus delta S of the system, and then we can calculate what is the delta S of the system is surroundings, I'm sorry, equals to, it's a minus delta H over T. As we know, the universe would divide into two parts, system and the surroundings, and the change of the entropy of the universe, it's actually is made of the changes of the entropy of the system and plus this change of this entropy of the surroundings. The second law of thermodynamics tells us that the process, that for a process to be spontaneous, the delta S of the universe has to be positive. For the spontaneous process, delta S of the universe should increase. And an equilibrium process is one that does not occur spontaneously in either the net forward or the net reverse reaction, but can be made to occur by addition or removal of energy to a system at equilibrium. So when you have a process which is at equilibrium, that means that the reaction really does not go forward or reverse, because at equilibrium, the rate of the forward reaction equals to the rate of the reverse reaction. But we can make a reaction to occur in any direction we want if we will manipulate, we will add energy or remove energy, depend on if the process is exo or endothermic in a forward direction. So now this one tells us determine if each of the following is spontaneous, spontaneous, or an equilibrium process at specified temperature. So they gave us A, B, C, D, several reactions, and that at the conditions given to us, this is a specified temperature at 0 degrees Celsius, 200, 1,000, and so on. So we can actually do our calculation. We can find out for this A process, we can find the entropy of the HI, standard entropy of HI. Well, of course, we have to multiply it by 2, subtract standard entropy of the reactants, and we'll see delta S equals to plus 21. Then we can find the delta H of a reaction, but we need to know the standard enthalpy formation of all the reactants and the products. And we can see that the delta H is minus 10.5 kilojoules per mole. Then we will see what is the delta S over surroundings. The delta S over surroundings is a minus delta H over reaction over temperature. So we will put the delta H with a negative sign, and the temperature was a 0 degrees Celsius over here, 0 degrees Celsius to 73 K. And we will see that the delta S over surrounding is the positive number. And then the delta S of the universe is delta S of the system plus delta S of surroundings. Then we will calculate the delta S of a universe, and the delta S of a universe is a positive number. So, and then because the delta S of a universe is a positive number, that reaction will happen spontaneously at 0 degrees Celsius. So once again, you will calculate delta S of reaction by having the standard entropies. Then you will calculate delta H of a reaction. But because delta S of the surroundings is a minus delta S H over reaction over T, you can calculate delta S over surroundings, add them together, you're getting a positive delta S for the universe. Reaction will happen spontaneously. So the same we will do for the others. So now the third law of thermodynamics tells us that entropy of the perfect crystalline substance at absolute zero or 0 Kelvin is 0. So, and this is the third law of thermodynamics. So the entropy can be 0 only at absolute 0. As the temperature is increasing, absolute 0 is a 0 Kelvin or minus 273.15 degrees Celsius. At that temperature, the perfect crystalline substance has only one position, to be at. And that, as you can see, if we will say logarithm of 1, it is, this is a formula, right? So K and the logarithm and the W's only has one position, just one position. The particles are arranged. So that will be equal to 0. That's the third law of thermodynamics. As the temperature starts to increase, now particles will have a different arrangement, 2, 3, and so on, and the entropy will be greater than 0.